Okay, we're going to look at something they call the Cartesian, also known as scalar equation of a line in two space. So let's look at this equation here. Y equals 4x plus 1. So that is in the familiar slope-intercept form, or y equals mx plus b. And we know the slope is 4. And we could also write that 4 over 1. And that was calculated by doing the change in y over the change in x between 2 points on the line. And the y-intercept, the b part, is 0, 1. It's the y-intercept. And we know that is where the line crosses the y-axis, but it's also a point on the line. Now, in the last video, we looked at creating an equation in vector form, and then from vector form, we could also go into parametric form. So let's take a look here. There is a way that we could go from slope-intercept form to vector form. So let's take care of the R naught part. So we looked at in the last video, R naught was just a point on the line. Now it can be any point on the line, but we have one available here, 0, 1. So I could actually put 0, 1 there for R naught. Now, I could, if I wanted to, I could pick any point, so I could go back up here and I could generate any point I want. But 0, 1 is there, so we can use that one, or any point that you choose. Now, the direction vector. Now, let's recall how that direction vector was calculated. So we know that was the change in x and the change in y between 2 points on the line. Well, if we look up here, where we had the slope, that's the same thing. Change in x, change in y between 2 points on the line. So I could take the 1 as a change in x, put it first, and the 4 as a change in y. Okay, and then if I wanted to, I can go into the parametric form. So again, it was xy. We saw this in the last video, but let's go over it again. So again, you're just separating the x component. So here would be 0 plus t. That would just be t. And y would be 1 plus 4t. And then again, like this right here, we saw in the last video, because of that parameter t, and behind the collinear vectors, I could have many different versions of the same direction vector. So if I wanted to, I could have 2, 8. Because 2, 8 is collinear to 1, 4, because I could factor a 2 out there. But again, you can go straight from slope-intercept form right to vector form and then to parametric form. Because that slope, change in y, change in x, is the same change in y, change in x, change in x, change in y, that they use for the direction vector. Now, I want to look at what they call Cartesian. I'm going to write that out. It can be referred to as Cartesian or scalar equation of a line. Now we have a little bit of experience with this already, so let's take that equation we were looking at, y equals 4x plus 1. So you might have heard, or it's been kind of maybe introduced to you, that when you have everything on one side, so I'm just going to balance out y and bring it over. So if I balance it to the right there, I only have to worry about the y. I can do it the other way also. But this right here, when you have everything in this form, so I'm just going to write it out, ax plus by plus c equals 0. So again, that in a previous course was introduced to you as standard form of the line. Same thing, right? It's now going to be referred to as Cartesian form of the line or scalar form of the line. So what you want to do is you want to balance everything to one side and have it equal to 0. But you can get something pretty useful from that form of the line, something we call the normal vector. So the normal vector is going to be a vector that's perpendicular to your line. So that means it's going to hit that line at 90 degrees. So if I make a quick little sketch here, intercept's 1, so that'd be about here. So then slope is 1 and then 4 up. Again, just oops, not too straight there. So I went 1 over and 4 up. Okay, so somewhere around there. So there's that line, y equals 4x plus 1. I'm just going to erase that part right there. So a normal vector is going to be a vector that is going to be perpendicular to that line. So go through that line at 90 degrees. So when it's in this form, when it's in Cartesian form, the normal vector, so for normal vector we're going to use this notation, n with the vector symbol. The normal vector is going to be these two coefficients, a and b, in that order. So in this case here, my normal vector of this line is going to be 4 and then negative 1. So let's see where that is. Again, remember, this is just a sketch here. But 4, negative 1, so that would be 4 over, and then negative 1. So then remember, it comes from, actually, probably a little bit, it's probably a little bit better here. So again, this vector here, again, this is sketch. This would be my normal vector, 4, negative 1. That is going to be said to be perpendicular. So again, this would keep going, right? That would keep going right through there. Try and do a little bit better job there. Sorry about that. A little bit better. So that would keep going through there and hit at 90 degrees. Now we can prove it, because we know that if you have two vectors and the dot product between two vectors is equal to 0, and they're said to be perpendicular. So I got the normal vector. So let me write that here. Now let's go back up here to when I had the line in vector form. So this one right here. So again, you want to use a direction vector here. So direction vector is that vector that's not perpendicular, but is parallel to the line. So again, the direction vector of that line was 1, 4. So let's do the dot product. 4 times 4 is 4. Negative 1 times 4 is negative 4. So that's 0. So again, that just proves that the normal vector, AB, when it's in Cartesian form, is perpendicular to that line. So you've got all these forms of a line. You've got slope-intercept form, vector form, parametric form, and now we just seen Cartesian, also referred to as scalar. This is not 4 different lines. This is 4 different ways of representing the same line. So again, taking into account what we know about direction vectors, what we know about slope-intercept form, what we know about change in y, change in x, and now seeing the normal vector. So normal vector is very, very useful, right? If you want to try and prove that two lines are parallel, you could look at the normal vectors and you could say, or look to see if they are collinear to each other. So can you factor something out to make it look like the other one? Same thing if you want to prove two lines are perpendicular, you could take their two normal vectors and do the dot product. And we'll be seeing that coming up in a couple examples. Going to save that for the next